We're going to continue looking at this concept of potential difference. The change in electric potential is called potential difference, and it's also called voltage. And again, we're defining voltage as change in electrical potential energy divided by charge. So our unit here is the joule per coulomb, and 1 joule per coulomb equals 1 volt. If we combine this equation with our formula for electric potential energy, where we said electrical potential energy equals negative QED, if I make a simple substitution, I end up with voltage equals negative QED over Q, or the Q's cancel, and I come up with this formula that voltage equals negative E, that's my electric field, times my distance. This is for uniform fields. If I'm working with point charges, we can combine Coulomb's law with our potential difference equation to get a formula for voltage around a point charge, and that's simply KQ over R. So again, I'd like to go back to this gravitational analogy and just remind you about what voltage really means. Voltage, we're saying, is negative E times D. And this E is my field. And again, my field has a strength and it has a direction. And it also has a shape, but in this case, the shape is a uniform one. And then here I've got a distance. And the idea here is that if I take a test charge in the field, and if I know the strength of this field, when I take that charge and move it, it's going to gain some potential energy. And what's really powerful about this idea of voltage is it doesn't matter if I'm working with one charge or working with a whole bunch of charges. Because if you have the same E field and the same distance, then you've got the same potential difference or the same voltage. And again, this is a really useful concept in current electricity. This is kind of like saying, if I go back to my gravity idea, I've got a ceiling and I've got a floor. If I've got a feather or a leaf, and if I've got a bowling ball, the thing that's different about those two objects is their mass, right? But there's something the same about lifting them the same distance. I've got the same field strength, G, and the same height change. So there's something the same there. And in fact, there's something else the same. We know that if I dropped these objects and there were no air resistance, they would both fall with an acceleration of 9.81 meters per second squared. So again, what we're doing with electricity is we're focusing on what's the same about these two things. And what's the same is the electric field and the distance that they are moved in that field. And that gives them what we call potential difference or voltage. Let's look at an example. Find the potential difference between a point infinitely far away and a point 1 centimeter from a proton. Now before I solve this, I want to determine, am I working with a uniform electric field or a point charge? And since it's a proton, I know that I'm working with a point charge, which means that for potential difference, I'm going to be using the formula KQ over R. What I'm interested in here is the potential difference created by this proton. Now, for a point infinitely far away, the potential energy at that location is 0. Just like if you have an object infinitely far away from the Earth, the gravitational force and the potential created is essentially 0. So what this question is really saying is that one of the points is basically 0, and therefore all I really have to worry about is the potential created by a distance of 1 centimeter. So now it's just plug it in and solve. 9 times 10 to the 9th for K. It's a proton, so my charge is 1.6 times 10 to the negative 19th coulombs. And then my distance is 1 centimeter, that's 0.01 meters. And when I solve that, I get something. I'll let you guys solve that. But my unit here would be volts. Okay, next for example 2, if 10 joules of work is required to move 2 coulombs of charge in uniform electric field, the potential difference present is what? Okay, so let's think about this. We've got work. Now work is the same thing as electrical potential energy. The work that you do is stored as potential energy. That's 10 joules. I know the charge is Q, 2 coulombs of charge. I'll call that big Q because that's quite a lot. And what I'd like to find is the potential difference, change in potential. So the formula is just electrical potential energy over Q. It's joules per coulomb. So 10 joules over 2 coulombs is simply 5 joules per coulomb, or 5 volts. So that's choice D. Let's try question 3. It says a charge experiences a displacement within an electric field from position A to position B. The charge, or the change in the electric potential energy is delta U, and the work done by the electric field during this displacement is WE. Then, now we're supposed to figure this out. Okay, so a couple of things. This sounds like, if I had to make a guess here, I would say this is a uniform electric field. So I like to draw a picture just so I can think about what it is that I'm actually working with. And I've got an object that's starting at position A and it's going to position B. And as it is moved from one position to another, it experiences a change in electrical potential energy. Now, I've been writing, for convenience sake, PEEL, but here they're saying let's use delta U sub E. Okay, and they're saying the work done by the electric field is WE. Okay, now we're supposed to come up here with an expression for voltage, essentially. So voltage is going to be the potential difference. They tell us that this object is moved from position A to position B. So let's be careful about our distance here, from A to B. So this is my initial, and this is my final position. And change is always final minus initial. So first of all, I know that I'm doing VB minus VA. So right off the bat, I'm going to cross out C and D as not being possible answers. And then the next thing that I'm going to do is compute, is think about what that means. So I know that voltage is equal to change in potential energy over the charge. So the change in potential energy in this problem is equal to delta U, and the charge is simply Q. So I think we have our answer here. It's E. All right, let's try one more. Question 4. Which of the points in this uniform electric field between the plates of the capacitor shown below lie on the same equipotential? Okay, what this means is the same potential. So, again, helpful to think about this as a ceiling and a floor. And where would you say the most potential energy in the room is? It's up here. And this is conventionally how we define high and low potential. We would say that the positively charged plate has the higher potential and the negatively charged plate has the lower potential. Just like in a room, if we're dealing with gravity, we would say the ceiling is where the high potential energy is. So the only pair of points that have the same potential energy are 2 and 4 because they have the same height. So our answer here is C. We'll be talking more about capacitors in our next section, section 18.3.